Okay, hi everyone. So this experiment is about Young modulus, that we want to find the Young modulus of materials. In this case is brass. Okay, for the objective, as I told you before, we have to demonstrate how to find the elasticity of the metal wires and to determine the Young's modulus of the metal wires. In this figure, if we have a wire which has the area of the circle and the length, the initial length is L0, and after that if we pull it with the force F, okay, in both sides, and then this wire can be extended and the final length is a bit longer. The length that is extended is delta L here. So we can define the tensile stress, which is equal F over A. And we can see the unit of the tensile stress is a Newton per meter square. Okay, Newton per meter square. In this case, A is the area of this metal wire. And then we can define the tensile strain by using this definition is a delta L over the L0. And this is unitless, okay, unitless. Because the dimension of the unit of delta L and L0 is the same, so it cancel each other. Okay. And now we can define the Young modulus, which is equal to the ratio of tensile stress to the tensile strain. In this case, the unit is a Newton per meter square, as same as the tensile stress. In general, for the metal or some materials, if we do the experiment, we keep pulling or stretching the material, it can be extended, and if we can measure the stress here, the stress will increase as well. Okay, sorry, the stress increase, so it make the material extended, so it makes strain. So at the beginning, we will have the elastic region where the material behave as a spring. So the relationship between stress and the strain will be linear. Okay, we call this elastic region. Okay, and then after that, if we keep pulling it, it will extend more, which we can define the plastic region where the materials extend but not tend to shrink back to the same length. Okay, and finally it will be broken, so we call it a fracture point. Okay, in this experiment we will study only the elastic region of a material. Okay, so we have the apparatus as showing here. We have the Young modulus experiment apparatus here and meter strip that we have to measure the length of the wire. Okay, the length of the wire, and we have the micrometer to measure the wire diameter because we want to calculate the area, so we need to know the diameter first. Okay, first we need to check the initial error of the diameter as we learned in the lab number 1. So from this figure you can measure the initial error of the micrometer. Okay, and then record in your data sheet. And next, please measure the diameter of the wire. Okay, we measure it for you, and then the number is somewhere here, so please read it and record in your datasheet. So in this case you can just use the same number for the 5 times of the measurement. Okay, because this is a virtual lab, I did it for you once, and then you use the same number. Okay, and then you find the average, and then the average plus the error, the initial error of the diameter, and then you can calculate the area by using this formula. Okay, this is just pi r square, but now r is a radius, right? So you got the diameter, so it's a 1/4 pi d square. Okay, for the y initial length L0, okay, I measure it for you, and I remember correctly, it should be 0.440 meter. Okay, 0.440 meters. Okay, because now we use the strip, right? The strip maybe I got 44.0 centimeter, so we can convert the unit into meter, but keeping the number of the significant figures. And next we set up the apparatus prior the measurement by using the following instructions. You can check here for the video demonstration. Okay, and next we stretch the wire by turning the hand wheel. So we turn the hand wheel 5 times. Each time we turn 0.05 millimeters, and then read the value as appear at the bottom of the Young's modulus test apparatus. Okay, this number has the unit of Newton, so you can record it in your datasheet directly. Okay, and then you can click here in your PDF file to see the video demonstration. And then next procedure, we stretch the wire 0.05 millimeter each time, and then record the value. So we do it stretch, right? Stretch 0.05, 0.10. 0.05 millimeter, and 0.10 millimeter, and 0.15 millimeter, and so on. So we got stretch, right, until the wire is stretched, had the stretch with the length of 0.30 millimeters, and then we turn the hand wheel in the opposite direction to shrink it, and then this number will be the same. This is at the 0.30 millimeter, and then we shrink it, right? So we got totally 12 numbers. Okay, 12 numbers of force that we can record in the datasheet. Okay, here the strain. The strain you can calculate using delta L. Maybe here delta L. Okay, delta L over L0. Okay, delta L over L0. So you can get the strain. And then for the tensile force, for example, at the 0.00 elongation is 0.00. Okay, 0.000, 0.000, and then average is 0.000. So the stretch is 0.00. But for the 0.05, you can record it as 1.440. Okay, this is 1.440. And then for shrink is 1.210, right? And then you can calculate the average value. Okay, the average value. Oh, what's happened? Okay, I'm sorry. Okay, we'll pause. Okay. Okay, and then you can find the average value for the tensile force for the shrink and stress. Okay, these both values, so you can find the average. And then you can calculate the stress. The stress you can find using F over A. Okay, and it will be in the unit of Newton per meter square, so please be careful about the unit. So you have to calculate the area in the unit of meter square first. Okay, so finally you can plot the graph. Using the space below and write down the title of the axis. For example, you can have this is like stress, right? Stress has a unit of Newton per meter square, and this is strain. Strain don't have the unit, and then you might get the data like this. Okay, so you can divide this is it, the strain, right? The strain, maybe you will have a 6 values of the strain, and then you also have a 6 value of the stress, the tensile stress. So you get some data maybe like this. Okay, you have 6 data, and then you can use your estimation by eyes, so you get the line, the straight line here. After that, you can calculate the slope, right? The slope of this line can be calculated using this relationship. It means you can pick any data that along this line and then calculate the slope. This slope is a Young modulus, and you have the unit of Newton per meter square. Okay, Newton per meter square. And for this plot, your data does not need to be on the graph, but it can be a bit above or a bit below. It's okay. Or if you are familiar with another method to plot graph, for example using Excel or Origin or Mathematica, you can use any software you like to get the slope, but please include the graph that you plot using that software when you submit your work. Okay, so in this experiment we use brass which have the Young modulus, the accepted Young modulus of 0.92 times 10 to 11 Newton per meter square. You have to use this value to calculate the percentage error here. Percentage error you can get by using this relationship. Percentage error maybe equal Young modulus experiment subtract with Young modulus except and then times 100, so you get the percentage error. Okay, so please show a calculation, the calculation for cross-sectional area of the y too. So it's a d square, right? So please substitute the numbers and calculate it. Okay, that's all. Thank you for watching.